Well, hello, I'm Gene Gard. I'm skipper of Ship 63 here in Birmingham, Alabama. And today we're going to go over some celestial navigation concepts for Sea Scouts, including the three main deliverables, so to speak, for the elective, for completing that elective. So the goal today of this session is really to give you the understanding of this concept. We're not going to go into tremendous detail about how to actually use the nautical almanac or the site reduction tables or things like that. There's infinite videos that are available on that matter, but I've taken, I think, 2 semester-long classes in navigation of various sorts, and 1 semester really focused on this. And I've used it aboard ships, aboard Navy vessels, and even to this day, I'm a little fuzzy on some of the details of how to actually use the various books and tables to produce the actual, navigational deliverables. But with that said, I understand the concepts, and that's 99% of the way of being able to do it. And if you understand the concepts, you can always refresh your memory on the details of actually using the books. And really the best way to do it is actually by attempting it when you're out to sea. So we'll just kind of go through some principles here. Just as a refresher, to understand this, you really need to understand basic navigation and the process of determining fixes. And essentially, the basic concept behind fixes is if you can get 3 lines drawn on a chart. In other words, if you see 3 different things and you can get 3 different directions from those things, then hypothetically where they all come together, that is a fix and it tells you where it is. And ideally, if you do it perfectly and everything works right with your equipment, all 3 of the lines, for example, in this case, should come together in one point. But you can see here, a lot of times there's a little bit of uncertainty and error, and so there's a triangle. But if you had these lines of position and had this on your chart, you'd be pretty confident you're somewhere in this vicinity right here. So the concept of celestial navigation is generally not much different than this, although there are some nuances to it and some kind of special tricks. But really, at the end of the day, you're just using the sun and the moon and the stars to produce lines of position, much like this. Although, as we'll find out, they're actually circles of position, but that still does narrow it down. So, yeah. So big picture, one way to think about celestial navigation is essentially we're on Earth, which is essentially a sphere. And then really it's almost like a shell surrounds us with all of the things in the heavens, so to speak, all the things in the sky. So you can see here this is a representation of that, and it kind of shows the stars. And it's important to notice that just as the Earth spins on its north and south pole, well, really that's what causes the stars to spin around us. So anything, if you're in the North America, or the northern hemisphere like we are, there's a certain set of stars you'll see because they constantly look like they're spinning around you. You'll really see the things that are above the this axis here. And you really won't see these stars much at all, and vice versa. If you're in the southern hemisphere, you really won't see the stars we're familiar with. So, that's kind of the fun. It's really that simple. When we talk about this navigational stuff, if you just have this model in your head, that is very useful to understanding celestial navigation. And in particular, every celestial body at any given time, and we'll talk about the stars here because that's, I think, the most useful, but we'll say every star at any given time has a geographical position. And to go back to this, this chart here, or I'm sorry, this picture here, for example, if we picked, it's pretty straightforward. On this outer shell, if we picked a star that's right here, there's only one place in the world at any given moment where it is directly overhead. And in this case, since we're kind of looking right at it, this particular star that I'm looking at here would be directly overhead to somebody, I don't know, in Colombia or something like that, somewhere in the northern part of South America. But at any given moment, that star is directly overhead for that person. So if you could see a star that was directly overhead and you knew which one it was and you had access to this information in these books, you would know exactly where on Earth you are. There's only one place you could be. But it's actually rare that you're directly underneath the star. So this particular star that I'm thinking about here, if you looked up and rather than being directly overhead, it was, say, 75 degrees above the horizon, well, then you wouldn't know exactly where you were, but you would know sort of within a circle. You could be down here looking up at the star there, or you could be over here looking west at the star. There's a circle of places you might be if you have an observation like that on a star. And one star is special. It's called Polaris, and the reason it's special is, again, if you go back to this concept, Polaris is one of the stars that's pretty bright and pretty visible, and it's most closest to right up there. It's closest to having its geographic position typically directly above the North Pole, more or less, which, as you can see, due to the way that our Earth spins, is pretty special, because basically if you can see Polaris at any time, and you typically can only see it in the northern hemisphere, but if you see Polaris, then that is pretty much north. Right? Like that, if you can see that star, it's somewhere up in the sky, and that direction is more or less north. And it can be a lot more tricky than that. And this is a really cool time lapse, but you can see here, I mean, who knows where this is? It appears to be in the ocean somewhere, but it's looking towards Polaris. It's probably on the beach or something. And you can see all the other stars appear to spin around because there are all these other stars that are, from our perspective, spinning around. But Polaris is about right there, and look, it doesn't spin around. It just kind of stays right there. So it's really kind of breathtaking for me to think about this, as kind of an abstract concept. But if you're outside looking at the stars, this is actually what's happening overhead. So it's a pretty cool concept. So again, we mentioned that the lines of position are circles. And you can see part of that depends on altitude, how high you are above the Earth's surface and a lot of other things. But, this is an example of a computer system that outputs this plot based on, sun and moon observations. And you can see that they are making a circle. So if you only have 2 observations of celestial bodies, and it's kind of weird again that this is sun and moon, usually it'd be a couple of stars. But you can see 2 observations are not deterministic in the sense that you could be up here or you could be here if you'd correctly done these. And of course, generally, in this day and age, you kind of know where you are. I mean, you'd have an idea probably if you were, and this one makes it easy because this one is actually in the water, and this one is somewhere in the highlands of Argentina. So you would probably know if you're in the ocean or not. But if you had this kind of plot and then you took a third observation and it made another circle that made the, they call it the peaked hat or something. I can't remember what it's called when it looks like 3 circles come together in one place. Again, just like with the observation we talked about of normal lines of position, if you get a third observation and it intersects right there, then you have a pretty good feeling that you're in the right place. So this is, just kind of out of the Sea Scout manual. And again, we're not going to get into the books, but there's really 2 books out there. And what those books do, it's the Nautical Almanac and the Site Reduction Tables. And basically what they do, this is what the Nautical Almanac looks like. It's always orange. This book tells you more or less, and you see you update it each year. You need a current one. Basically for the sun and the moon and a whole bunch of different stars, which are generally selected because they're bright and visible in the night sky in North America. I'm sorry, I keep saying that, in the northern hemisphere. This book basically at any given time, with some interpolation and stuff, can tell you essentially what the geographic position is of every celestial body in the sky, which is pretty cool. And that's helpful, but then that doesn't quite get you there. So you need some way of figuring out, if you see a star in the sky, what its geographic position is, but then you need to figure out how that tells you where you are. And that's what this second book does, these site reduction tables. They help you figure out that answer. And you can see they're pretty long, and for example, this one is only for certain latitudes. They're all for certain latitudes, but these are books that you'll have especially if you're on a sailing vessel, but really any modern ship that goes to sea should have these this kind of material available just to be useful in an emergency when your GPS might not work, but also just in general to keep up with this, because it's just also a really cool thing. So And this is an example of, you can see this is the part of the Nautical Almanac that focuses more on the planets, which are also, very useful navigational things if you can see them. And then you can see here, these are some of the stars, which is kind of cool. They all have names. And I think we even have a slide later that talks about some of the more popular ones. But, most of these are parts of different galaxies. So, Altair is a big one. Deneb, everybody's favorite is Betelgeuse. It's usually in there. Vega is another bright one. So those are all important. Yeah, and again, this just kind of shows you some more detail from that. And then this is the site reduction tables, which are a little bit more boring. So, a local angle a local hour angle is something you'll see. Also, I think a Greenwich hour angle, and that all has to do with how far from the prime meridian, your observation is. And again, there's tremendous amounts of material on actually interpreting these. And again, this is some of the more popular stars that are easy to recognize as parts of constellations, and then also that are relatively bright, which are kind of the two most important things when you're figuring out this kind of stuff. So as far as the actual Sea Scout elective requirements, you can see that there's 3 requirements here. One is explain how a sextant works. One is find your latitude on the Earth either by Polaris or local apparent noon. We'll talk about that. And then how you figure out longitude, which is actually a pretty cool historical puzzle that was solved. And then this last one is kind of a strange one. I mean, it's very specific, but we'll look at that one too, just for purposes of meeting the requirements. So as far as how sextants work, I actually have one here. These are things that can be very expensive. They're very much precision scientific instruments. But this is a pretty popular one. This is a Davis Instruments one. I don't know that they're made anymore. The one I have was made in the 70s. But the box looks like this. But essentially, this is a plastic one, which, I guess isn't ideal. But these are pretty reliable, and, many very real observations have been taken by these on sailing trips and things like that. And essentially all it does is it allows you to see something in the sky, and based on the horizon it'll tell you how many degrees above the horizon whatever it is you're looking at is. Essentially you look through at a mirror, and we actually have something to show you how it actually works, but then you adjust this part until the thing you're trying to observe rests on the horizon in the mirrors that you see. They're sort of side by side. And that's all it does. It just determines how high in the sky the object is. So I think we actually have a little video here if you can see it. You can see the horizon on this side, and then if you're taking a sun observation, you bring the sun to the horizon, and then you kind of twist it around to make sure it's right, and then you read the angle, and that's the answer. And there are filters, for you, so you don't have to look directly in the sun or the mirror image of the sun. But that's really as simple as it is, and these have existed for many hundreds, probably thousands of years. But it's that simple. They simply, whether it's the moon or the stars or a planet or the sun, it tells you how high above the horizon it is. Yep, so this observation, find the latitude or by the altitude of Polaris or by the sun's altitude at local apparent noon. Demonstrate how longitude is determined. Well, that's the whole thing. But we'll talk first about latitude from Polaris. Again, as a reminder, way up in the heavens, Polaris is up here. And so what's pretty cool is with a couple of minor corrections for things like how tall you are, how high you are, either due to your height or your ship is above the horizon, based on your height and some refraction from the atmosphere numbers. Essentially, the altitude of Polaris is just your latitude. Because if you think about it, if Polaris is 90 degrees above you, then you are at the North Pole, so you're essentially at 90 degrees of latitude. All the way down to where if Polaris is just barely on the horizon and it's close to a zero elevation from you, then you're probably close to the equator. And just because of the way geometry works, if it's 30 degrees above the horizon, you're probably somewhere in North Africa, the Middle East there, somewhere around there. So it's pretty cool. And again, you can look up videos or Google. It's very simple to, find the documents and understand, how to make those minor corrections. But that's the fundamental answer. And let's talk about local apparent noon, because local apparent noon is a pretty cool thing as well. And going back to this picture, if you think about it, wherever you are in the world, if you watch the sun, when it rises, in the first thing in the morning, it'll be right on the horizon, obviously, and when it sets, it'll be right on the horizon. However, depending on where you are, it may never quite get directly overhead, depending on the seasons and everything, and we'll ignore the seasonality of it. But if you think about, generally speaking, if the Earth didn't tilt back and forth and have seasons and everything, if you watch the sun and then figure out when it stops getting higher in the sky and starts going lower, that is local apparent noon, which is the highest point the sun will ever be throughout the day. And again, if you think about the Earth as a big ball, if the sun does get directly overhead, then you're probably somewhere close to the equator or, the tropics, depending on the time of year. But for these purposes, we'll just assume that you're close to the equator. And vice versa, if the sun barely gets up in the sky at all or doesn't rise at all, there's periods of time when, like midnight sun or vice versa, it never gets light. You might be very close to the poles. But generally speaking, if you know what time of year it is and you know how high the sun is at local apparent noon when you use your sextant to take observations around noontime, then you can figure out exactly what your latitude is. Again, you don't know where east or west you are on the Earth, but you know exactly, within a margin of error, how far north and south you are, which is pretty cool. You can see some more detail here. It talks about the observed altitude and declination. So the sun's declination is its angular distance north or south of the celestial equator. So in other words, that essentially adjusts for seasons, right? Because if you're somewhere, just because the sun is directly overhead doesn't mean you're on the equator because of the seasons, because of the tilt of the Earth back and forth. So, with this information, that's how you figure out what the latitude is where you currently are. So this is a pretty cool thing. And again, this has been available to people for hundreds of years. 1,000 years probably. We've rediscovered over time, discovered and rediscovered the idea that the Earth is not flat, but people that understood that could understand this even, without too much additional technology. So this is actually really cool, and I'll just go back to the picture before I do the spoiler alert. But this was a major problem, and I think this was even a problem, up until relatively recent history. The last, I think maybe the 1700s, 1600s, 1700s, maybe they were still trying to figure this out. Because we learned there's several different ways to figure out how far north or south you are, but it's much more difficult to figure out where you are east and west. Because of the way that the world works and the way that it rotates on the axes, that's a much harder problem to solve. And the person who solved it, I think it was through the Royal, British Society in England. It was the guy that finally figured it out. But essentially, you can figure out exactly how far east or west you are in the world if you just have a clock, and if it's a reliable clock. And you know this intuitively, because if you think about it, looking at the map here, and we'll start over here in England because that's where this stuff kind of came up originally, and this is the GMT, the Greenwich Meridian line, basically the prime meridian. So if it's noon over here in England, well, there's a place in the world that's 180 degrees out, which of course is somewhere in the Pacific Ocean, where it's midnight at that time, and vice versa. So, if you're over here in the world and you observe local apparent noon, well, if you know that it's midnight in Greenwich, England, then you're essentially exactly 12 hours out from England, and also that you're essentially on the opposite side of the world. And this works all the way around. And so I can show you this. Let me just pull my calculator over. So if you think about it, going around the world, there's 360 degrees. So, well, you already see I did the math. But if you take 360 degrees divided by 24, well, that's 15 degrees per hour. So in other words, if you took local apparent noon and it was exactly 1 hour different than Greenwich noon, in other words, if it's noon where you are and it was 11 o'clock or 1 o'clock in Greenwich, England, then you would know your longitude is about 15 degrees out one way or the other. And of course you could figure out which direction by what time it is. But it goes all the way around. So if you're 6 hours out, you're probably somewhere in the Gulf of Mexico or something, or I don't know if there's much ocean over there, but you get the idea. If you can keep track of time, then you know where you are east and west. And of course, this is not a easy problem to solve, because making a clock that would keep time for weeks or months or even a year or more at a time was a pretty tall order. And of course, you would know how much the time would change based on if you knew your clock lost 6 seconds every day, if you kept track of the days, you could adjust it over time. But essentially, the development of clock timekeeping was really the technology that allowed people to figure out where they were in the world before there were nautical almanacs and site reduction tables and things like that. And so again, you can see, so every 4 minutes of time is 1 degree of longitude, or 15 degrees per hour. So that's pretty cool. The last requirement for the elective is demonstrate finding error in the boat's compass by the sun's azimuth. And so this is, again, this is a pretty specific thing, but we'll go through this. So this is what they mean. Typically, if you are on a big vessel that actually has a gyro compass, a big magnetic compass or compass repeater, it's a big thing. It's kind of like a plate you look in, and there's glass on top, and you can see what direction things are, and there's things so you can shoot directions from it and figure out. We talked about way up at the beginning. You can figure out these. That's the main way that you create these lines of position. If you see a windmill or something on the shore, and you use your compass to point at it and figure out it's 290 degrees out, that helps you draw these lines to figure out where you are at any given time. So let me scroll back down. Sorry, the Google presentation doesn't work quite like PowerPoint. So anyway, if you have one of those compasses, you can put this thing over it, and it helps you. It uses some mirrors and things to help you figure out exactly what the direction is from the sun at any given time. In other words, if you can figure out the exact direction to the sun, and it's called an azimuth. So you can see here, if you're here at any given time and the sun is up in the sky, there's two ways to define where it is. One is how far over it is, and then one is how far up it is. So how far up it is the altitude, and how far over it is the azimuth. And so this just allows you to, given the fact the sun's in the sky and you're not, it lets you figure out what that azimuth is. And so if you shoot an azimuth to the sun at any particular time, like the top of the hour, or half after an hour, or 15 minutes or something, you can then use the information in the nautical almanac and what you think your position is to tell you what the azimuth to the sun should be. And then, of course, because of your compass, you have a compass here, it tells you what the azimuth actually is. And what that allows you to do is it helps you calibrate your compass. So in other words, there's all kinds of reasons, and you'll get into this if you ever get seriously into the navigational stuff. There's all kinds of reasons why your compass might be a little bit off. And there's magnetic issues and problems with the magnetic signature of your ship, and just general, there's all kinds of things that can make the compass be a little bit off. But this tells you exactly, it's a way without fancy calibration equipment to test your compass and see what the error correction should be. And so if your calculation is that the azimuth to the sun should be 172 degrees and the compass is telling you it's 171 degrees, then you would know to correct your compass observations by 1 degree, for example, 1.0 degrees, to figure out the best direction. So again, this is something you can find plenty of other videos to go into more detail on, but I think it's important to understand the concept behind it, because if you understand the concept, you can always figure out which tables to look up or which computer program to use and all that kind of stuff. But this is the real understanding is just being able to think this way with this kind of sketch. So anyway, that's a very brief introduction. Like I said, you could go into a lot more detail, but for many people, this should help you get this stuff in your head, and hopefully it's useful. And good sea scouting, and Bravo Zulu.